Today's class, I am going to discuss about delay unit, inverter delays, such as NMOS inverter, CMOS inverter delays, and estimation of CMOS inverter delays, that is rise time estimation and fall time estimation. In previous class, we have seen that sheet resistance concept and standard unit of gate capacitance, that is square CC, right? Here I want to consider these two concepts for the implementation of or for the calculation of delay in it. Okay. So here the delay in it is nothing but it is the time taken to reach the response, that is 63% of response from the, that is 63% of final value from the initial value is nothing but delay in it, right? And that concept is here. I want to calculate inverter also here, that is NMOS inverter delays and CMOS inverter delays. But one thing here, the NMOS inverter is going to be connected in cascaded form, and then we have to calculate the delay response. Means how much amount of time it is taken to generate the response at the output time, right? So here, firstly, it is delayed in it. So the delay in it, this is the figure here going to discuss about this concept here. So this is the past transistor. Okay, here the gate is fixed at VDD, means the transistor is on condition, right? It is in on condition. And here the NMOS minimum size pass transistor on resistance is 10 kilo ohms. Okay, so here when the VDD is at gate, it is in on condition. Here I want to apply VDD input response. So this VDD is going to be just pass from one point to this point to this point to this point, right? So here this output, the pass transistor is going to be connected to the input of the another N channel device. So here, so this response is going to be charged. This response is going to be changed from 0 to VDD, right? So here, this much of time here, this point, nothing but the time taken to reach the response, that is 63% of final value from the initial value, nothing but a delay in it, right? So here, this is the time constant, time delay in it. So the response is taken to change to reach 63% of final value from the initial value, right? So here I want to see in this point here, we have developed the concept of sheet resistance RS and standard gate capacitance in it 1 square CH, right? If we consider the case of one standard unit future size square gate area capacitance being charged through one feature size square of channel, that is N channel, the resistance is nothing but the resistance, then we have tau. Means here the transistor is in resistance mode, then only the capacitor is going to be charging. So how much amount of time it is going to be taken to charge the capacitor, nothing but delay in it. Okay, you know that already I told you the delay in it means nothing but it is the time taken to reach the 63% of final value from the initial value is known as delay in it. Okay, generally you know that the time constant, that is tau equal to R into C, right? R into C. So here the capacitor is going to be charged. How much amount of time it is going to be charged or discharged, that will be depending upon this resistance value, right? If the resistance value is very high, the capacitor has to be taken very large amount of time to charge. Okay, if the resistance will be very less, so means the capacitor is taken very less amount of time to be charged, right? So here instead of this R and capacitance, I want to take, that is resistance, here it is sheet resistance, right? Sheet resistance, and the capacitor nothing but standard gate capacitance square CG, that is nothing but delay in it, right? So this is here I want to I shown here time constant tau equal to 1 RS, that is for N channel, and 1 square CG, that delay unit is nothing but represent in seconds. right? Also calculate the delay unit for various technologies here. We know that technologies are nothing but 5 micrometer technology, 2 micrometer technology, and 1.2 micrometer technology, right? 1.2 micrometer technologies. So I want to calculate the delay unit for 5 micrometer technology. We know the values, so such as nothing but resistance value for 5 micrometer technology, that is RS equal to 10 to the power of 4 ohms. And the standard unit of capacitance for 5 micrometer technology, that is 0.01 picofarads. So we know that tau equal to delay unit tau equal to RS into square Cg. So multiplication of capacitance value and sheet resistance value, nothing but it is delay unit, right? So therefore tau equal to 1 RS into square Cg. That is in, it is in the units is nothing but seconds, right? So here the tau equal to, you can substitute the values here, RS value and standard gate capacitance value in this, instead of RS and CG values, that is RS is 10 to the power of 4 and CG value 0.01 picofarads. Okay, so here the tau is delay unit in 5 micrometer technology that can be represented in seconds. So here pico is nothing but it is represented as 10 to the power of minus 12. So finally, that is tau in 5 micrometer technology, that is 10 to the power of 4 into 0.01 into 10 to the power of minus 12 seconds. Okay, so therefore the total time delay in 5 micrometer technology, that is the delay unit is nothing but it is 0.1 nanoseconds. Similarly, for 2 micrometer technology, the seed resistance for 2 micrometer technology is 2 into 10 to the power of 4 ohms. And that is the another concept, another parameter is standard unit of gate capacitance, that is square Cj, that is 0.0032 picofarads, right? We know that tau equal to RS into standard gate capacitance value, that is in represented in seconds, right? And tau equal to that RS value is 2 into 10 to the power of 4 ohms. Okay, 2 into 10 to the power of 4 into square Cg value, that is 0.0032 picofarads. So 0.0032 picofarads. So here the tau is for 2 micrometer technology, that is 2 into 10 to the power of 4 into 0.0032 into 10 to the power of minus 12. So here 10 to the power of minus 12 nothing but instead of pico here, and it is represented in second. Okay, so therefore for 2 micrometer technology the delay unit is 0.064 nanoseconds, right? And one more technology, that is 1.2 micrometer technology. Here for this technology the seed resistance value is, that is 2 into 10 to the power of 4 ohms. And the another parameter is standard unit of gate capacitance, that is 1 square Cg, nothing but 0.0023 picofarads. But we know that the tau equal to 1 RS into 1 square Cg in seconds, right? You can substitute the RS value and Cg value in this equation, then tau equal to 10 to the power of 2 into 10 to the power of 4 ohms into 0.0023 picofarads. Okay, you can change these picofarads in seconds, then tau at 1.2 micrometer technology, that is equal to 2 into 10 to the power of 4 into 0.0023 into 10 to the power of minus 12 seconds. Okay. Finally, the time delay unit for 1.2 micrometer technology is 0.046 nanoseconds. Right here, this is the gate capacitance. Gate capacitance, meaning nothing but how much amount of time to take into charge the capacitance value across the device. Okay, suppose here if we consider the wiring capacitances, then the delay unit value will be twice or 3 times than the actual values, right? Next thing is, here it is NMOS inverter delay. So here it is inverter delay. Okay, here consider the circuit diagram. Here the NMOS inverters are connected as in pair form, nothing but they are connected in cascaded form, nothing but here it is called as a pair delay, right? So consider the inverter here. Okay, consider the basic 4:1 ratio NMOS inverter are connected in series. The delay through a pair of similar NMOS inverter. Okay, so here I want to calculate the delay through this pair of similar inverters. So how much amount of time to taken to change to generate the output response at final stage, that is nothing but inverter delay. Okay, for that I want to calculate here. So this inverter is represented in this form here. So just you have to see observe this diagram here. So this is the first part, and this is the second inverter, right? So here the inverter response is going to inverter's internal circuit diagram, that is nothing but it is pull up transistor, it is nothing but pull down transistor, right? Similarly it is pull up 2 and pull down 2, second part, second inverter, right? Consider here for NMOS inverter, here the Z pull up to pull down ratio is 4:1. Z pull up to pull down ratio nothing but here Z pull up to pull down ratio is nothing but 4:1. Here 1:1. It is pull down transistor, it is pull up transistor. Therefore here the Z pull up by pull down equal to 4/1. Therefore Z pull up equal to 4 into Z pull down, right? So let us observe here in the circuit diagram. Here if the input response is VDD, input response is given at the pull down transistor 1 is VDD, then the pull down transistor is going to be on condition. Okay, here it is the pull up device nothing but it is the resistive region. Resistive region means it is on condition, right? When the pull down device is going to be on condition, so whatever the value having across this gate capacitance value, that will be discharged to ground, discharges to ground through pull down transistor. Finally we have the value here, it is 0. That 0 is given to the input of second inverter. So then the pull down transistor 2 is going to be off condition, right? So then here when the pull down transistor is off condition, so then the pull up is always on condition, means it is in resistive region, it is in resistive region. Now the capacitor is going to be charged VDD, capacitor is going to charge VDD through this pull up transistor or pull up resistance, right? So let us observe here the points. Here we are observed two cases, such as one is if the V input is 0 volts, then the pull down 1 is off and the standard gate capacitance CG is charged to VDD through a pull up resistance, right? So let us here, suppose here I want to apply input is 0, then this transistor is pull down transistor 1 is going to be off condition, then that case the capacitor is going to be charged through pull up transistor, right? Suppose here if I want to apply V input is VD, then the pull down transistor is going to be on condition and the standard gate capacitance CG is discharges to ground through the pull down transistor, that is the square CG. That square CG nothing but it is equal to 0 volts. Okay, so therefore the delay unit for first case, that is if it input is VDD is V input is VDD, so then the tau 1 is nothing but Z pull down into square CG. This is nothing but equation number 1. Okay, so why I am going to form this equation here. So here when the input voltage is VDD, okay, then when the input voltage is VD here, the pull down 1 is going to be on condition, the capacitor is going to be discharges to ground through this pull down transistor. So here this is nothing but pull down, Z pull down, okay, Z pull down into square CG, nothing but tau 1, right? So here Z pull down into square CG. Here the Z pull down is nothing but I want to represent with the RSN. Okay, RSN, resistance value, seed resistance value for N channel. Similarly, after the capacitor discharges pull down transistor through the pull down transistor 1, if it is off condition and the second inverter input is 0 volts, then the output capacitor will charge to VDD through the pull up resistance, right? So here if for the input voltage VDD, finally we are getting the output response of this output response of the first inverter is 0. So this 0 is applied to the second inverter. So due to this input is 0, the pull down transistor is going to be off condition. Pull down transistor is going to be off condition. So at the same time, the pull up transistor is pull up device on condition. The capacitor is taken to charge VDD towards VDD through this pull-up transistor. Through this pull-up transistor, then the tau equal to Z pull-up into square CG, right? Square CG. So let us see here. This it is the point here, that is second part inverter tau 2 equal to Z pull-up into square CG, that is equation number 2. But our aim is here to calculate the total delay for cascaded pair of inverter, right? So therefore, the total delay equal to sum of the equation 1 and equation 2, then we get tau equal to Z pull down into square CG plus square CG plus Z pull up into square CG. So add the equation 1 and equation 2. Okay, so here I want to take out common point here, that is Z pull down and square CG. So then here it is 1 plus Z pull up by Z pull down. Why? Because here there is no Z pull down here. Okay, only Z pull up is available here, and I want to take common here Z pull down. So then Z pull up by Z pull down is occur, right? This formation. But we know that Z pull down equal to 1 RS. So instead of this Z pull down, I want to replace that is with 1 RS. Therefore, tau equal to RS into square CG of 1 plus Z pull up by Z pull down. Okay. Therefore, the total delay equal to tau of 1 plus here tau nothing but, so this part are nothing but tau equal to time constant, nothing but it is R into C, right? So here tau of 1 plus 4 by 1, that is equal to finally it is 5 tau, right? This is the total delay for inverter as connected in cascading node form. So hence, if NMOS inverter is connected with another NMOS inverter cascaded form, for this the total delay is 5 tau, right? And next case here it is CMOS, right? Here, okay, here it is CMOS inverter delay. Okay, so here let us see, this is the CMOS inverter, first inverter and second CMOS inverter. Those two are connected in cascading form. So let us see here, it is 2 square CG, but in the previous case there is a 1 square CG. Here why it is 2 square CG? Here nothing but here one is P channel and the one is N channel. There are 2 capacitance are going to be charges. Likewise here it is going to be 2 square CG, right? So here let us see here. So this is the first part of CMOS inverter. This is the second part of CMOS inverter. So here pull up 1, pull down 1, pull up 2 and pull down 2, right? So let us, before going to be this operation of the circuit diagram, I want to check this point here. If V input is 0, right? If V input is 0 here, so if V input is 0 here, so then PMOS is going to be on. Nothing but pull up 1 transistor going to be on. Okay. Here and NMOS is going to be off condition. So this is NMOS is going to be off condition, right? So then the capacitor is going to be charged, right, towards the VDD, towards VDD, right, through the pull-up transistor 1. Suppose, okay, here the capacitor is going to be charged, right? Here the capacitor is going to be charged towards the VDD through this pull-up transistor 1. So here the response here nothing but VDD. The response is nothing but VDD. So this VDD is going to be applied for the second inverter. So then the PMOS is going to be off condition, NMOS is going to be, that is pull down 2 is going to be on condition. Then the capacitor will be discharged through this transistor pull down 2. Okay, that is the first case. For second case here, if V input is VDD, then the PMOS is off condition and the NMOS is on condition. Then the capacitor discharges to ground through pull down resistance, that is Z pull down. Okay, if the second case V input is VDD, then the pull up transistor 1 is going to be off condition and the pull down transistor is going to be on condition. So whatever the L is having across this capacitor, that is discharges to ground through this pull down transistor 1. So finally we have the value here, it is 0, right? Here finally we are having the value here, it is 0. That 0 will be applied at the second case of inverter here, that is then the pull up transistor is going to be on condition and pull down transistor is going to be off condition. So then the capacitor is going to be charged towards the VD through this pull up transistor. Okay, for the first case here, suppose here the capacitor is going to be the capacity going to be charges discharges to the ground here. So then the tau 1 equal to ZPD 1, jet pull down 1, means the capacity is going to be discharged through this pull down transistor 1 if the V input is voltage is VDD, right? So then tau 1 equal to ZPD 1 into 2 square Cg. This is the value. Okay, the time constant equal to R into C. Likewise here ZPD 1 into 2 square Cg. So here ZPD 1 nothing but RS value for pull down transistor 1. So now here the voltage at a second inverter is 0 volts. 0 volts. Now the capacity is going to be charged towards VDD through the pull up transistor 2, right? Pull up transistor 2, that is pull up to resistance. Means here by applying 0 as input for the second case, then the pull up 2 device is in resistive mode, right? Now then the delay unit, that is tau 2 nothing but jet pull up 2 into 2 square Cg. So this is a number, equation number 2. But our aim is to calculate the total delay for this CMOS inverter pair delay. That is, so that is to add the equation 1 and equation 2, then only we have to calculate the total delay for CMOS inverter pair delay, right? So here the total delay equal to ZPD 1 into 2 square Cg plus Z pull up 2 into 2 square Cg. But we know that Z pull down 1 equal to Rn, that is equal to 10 to the power of 4 ohms, and also it is equal to, it will be converted into 10 kilo ohms. Similarly, Z pull up P equal to RP, that is P channel, that the value, resistance value for P channel is 2.5 into 10 to the power of 4 ohms. So it is converted into kilo ohms, that is 25 kilo ohms, right? So when the Rn and Rp are the sheet resistance values for NMOS and PMOS for 5 micrometer technology. So therefore, Rp by Rn equal to 25 kilo ohms by 10 kilo ohms, that is equal to, the value is 2.5. Therefore, Rp equal to 2.5 into Rn. Okay, we know that the total delay equal to okay, tau d equal z pull down 1 into 2 square Cg plus z pull up 2 into 2 square Cg. So now I want to replace these values, that is z pull down 1 and z pull up 2. Okay, so here z pull down 1 is nothing but RSN or RN, and z pull up 2 is nothing but RP. Okay, so instead of that, I want to change this term. Total delay equation is tau d equal Rn into 2 square Cg plus Rp into 2 square Cg. Okay, now I want to replace these values, that is Rn value and Rp value in this equation, right? So tau d equal to Rn into 2 square Cg plus 2.5 Rn into 2 square Cg. So here instead of Rp, you can substitute 2.5 Rn, right? So here the common point is Rn into square Cg. Okay, Rn into square Cg. Okay, so here common point is Rn into square Rn into square Cg. So here 2.5 into 2 nothing but 5. So finally tau d equal to Rn square Cg of 2 plus 5, that is 5 tau. Therefore the total delay for to get the output response at the final stage, that is that amount that delay unit nothing but tau d equal to 7 tau. So 7 tau amount of time to take in to get the output response at the final stage. Okay, and the next concept is a formal estimation of CMOS inverter delay. Okay, you know that the rise time and fall time analysis here, that is nothing but rise time means nothing but charging time, and fall time nothing but discharging time to the load capacity, that is CL, right? CL. So here the time rise time nothing but represented with the tau R, and fall time is represented with the tau F. So I want to analyze this rise time analysis and fall time analysis as estimation here. Okay, the rise time nothing but in this analysis we assume that the P device stays in saturation mode. Okay, so here you know that the circuit diagram CMOS inverter, suppose here it is the CMOS inverter circuit diagram. So it is PMOS transistor, and this is NMOS inverter, NMOS transistor. Commonly I want to take it as a common output terminal, and the drain is going to be output response, output terminal, right? So this is a VDD, right? This is VDD. Here it is common gate is nothing but V input, and this is nothing but VSS, right? So here in this analysis, we assume that P device stays in saturation mode. Saturation mode means if I want to apply input is 0, then the PMOS is going to be on condition. If it is saturation mode, then the current flows across the device is IDS, drain to source current for P channel, right? It is in saturation mode, then the current will be flows across this device, nothing but IDSP, right? So here, then the entire charging period of the load capacitor is CL, right? See here, okay. So here, this is the IDSP. So this is the IDSP for saturation mode. We know that the current equation for saturation mode, it was taken from the that is relationship between IDS versus VDS for the mass transistor, right? So here IDSP equal to beta P of VGS minus modulation of VT whole square by 2. Okay, so this amount of current will be charge across this load capacitance, right, across the CL. Okay, so here, so this is circuit diagram. So when input is zero response, zero input is given here, that the N channel is going to be open circuit and P channel is going to be short circuit here. So means it is in saturation mode. Then the current flows across this PMOS device, that is nothing but IDSP. So such amount of current is going to be charged across this capacitor. So finally we get the response is output is 1 for input is 0, right? So here this current charges CL, and since its magnitude is approximately constant, we have V out equal to IDSP into T by CL, right? So we have here the IDSP value can be substituted instead of this here. You know that IDSP value beta P of VGS minus VT whole square by VTP whole square by 2, right? So here we want to substitute IDSP value instead of this case. So V out equal to beta P into VGS minus beta P of VGS minus VTP whole square by 2. So then this equation changes here like this. So T equal to, that is nothing but time taken to charge, that is 2 into CL V out by beta P of VGS minus VT whole square, right? So we assume that T equal to tau R, nothing but it is nothing but rise time analysis, and here V out equal VDD, and similarly VGS equal to VDD, right? You can substitute these values, and also VTP is 0.2 VDD. So you can substitute this value in equation here, tau R, that is rise time analysis. So here 2L into, okay, 2L into VDD by 2CL into VDD by beta P into, right, beta P into VDD minus 0.2 VDD, right, VDD whole square, right? But finally we get this value 2CL VDD by beta P into that is 0.64 VDD, okay, 0.64 VDD whole square. Okay, you can cancel this square into VDD here, and 2 by 0.64, nothing but that is equal to 3.125 like this. So for this 3.125, so I want to consider here TR equal to 3CL by beta P VDD, right? Similarly, for fault time analysis here, estimation, so fault time means here input is 1, then the pull down transistor, that is nothing but N channel, is going to be resistive region. So whatever the value is available across this load capacitance, that will be discharges to ground through this N channel. Finally we get the value at the output side is 0, right? For making this assumption, we know that similar assumption for, we may write fault time analysis tau f equal to 3 into CL by beta N VDD. Okay, for summary of CMOS rise and fall time factor, tau R by tau f equal to beta N by beta P. Okay, so here the mobility of the but here you know that the mobility of electron is that is equal to 2.5 mobility of the holes. So here you want to remember one point here, whereas here the fall time analysis is very less amount of time to take in to discharge the capacitor, and for rise time the capacitor is going to be charged, it was taken very large amount of time because of there is a mobility of the charge carriers moment, there is a difference of mobility in between n channel and p channel, right? So in n channel the mobility of the electron is more compared to the mobility of the holes in the p channel. So for equalization of the rise and fall time analysis, we want to increase the mobility of the charge carriers in the p channel. That is the only way here it is available to increase the width of the p channel, right? And hence beta n equal to, that is geometrically equal to 2.5 into beta p, so that the rise time is slower by a factor of 2.5, right? Slower than by a factor of 2.5. Okay. And here, in order to achieve symmetrical operation using minimum channel length, we would need to make WP equal to 2.5 into W1. As I told you here, that is to increase the width of the P channel, then only we can get the symmetrical operation or symmetrical assumption for this delays for rise time and fall time, right? And this inverter having an input capacitance for n channel, it is that is 1 square Cg, and for p channel it is nothing but 2.5 square Cg is the time for n channel and for p channel and n channel here. So total it is to be 3.5 square Cg, right? It is the time to take in for input capacitance for this